You will see throughout Chapter 9 this term like dissolve like. And basically what that means is a polar solvent, such as water, will dissolve a polar solute, such as ethanol, sodium chloride, or sucrose. And a nonpolar solvent, such as turpentine, will dissolve a nonpolar solute, such as oil paint or grease. Now you've probably seen oil and water and noticed that the oil kind of clumps together in droplets. That's what's known as a hydrophobic effect. Hydrophobic molecules are actually nonpolar molecules. And literally, hydrophobic means water hating or water fearing. And of course, molecules have no emotions. So hydrophobic is just another word for nonpolar. And nonpolar molecules cannot hydrogen bond. So in this graphic up here, we see these little water molecules that are connected by the dotted lines, which means they are hydrogen bonding. And this larger gray images represent nonpolar molecules, hydrophobic molecules, oil molecules. They cannot engage in hydrogen bonding. So what the nonpolar or hydrophobic molecules will do when they're placed in water is they will gravitate toward one another to minimize their interaction with the polar solvent. And at the bottom of the graphic, we see an image of oil in water. Now, nonpolar molecules or hydrophobic molecules cannot engage in hydrogen bonding. We remember from previous chapter that only polar molecules can engage in hydrogen bonding. However, intermolecular forces do occur between nonpolar molecules. That's what keeps these two oil molecules together, what allows oil to clump together when it's in the presence of water. And those intermolecular forces are known as dispersion forces. And dispersion forces are the only intermolecular force that nonpolar or hydrophobic molecules can engage in. Now, dispersion forces increase with increasing number of electrons. We'll see in a minute how dispersion forces are related to number of electrons. But the more electrons you have, the stronger the dispersion forces are. And an easy way to kind of gauge how many electrons you have is molar mass. The higher the molar mass of a molecule, the more electrons there are. So as the number of atoms or the molar mass increases, so does the dispersion force. So how does this dispersion force work? Well, like hydrogen bonding, it is an attractive force. However, it is far weaker in terms of its charges than hydrogen bonding is. Dispersion forces result from electron density fluctuation, forming an instantaneous dipole. So what does that mean? So on this graphic here at the top, we see these two spheres which have the same color and represent two molecules, two nonpolar molecules. At any given time, so that's what we mean by instantaneous, electrons may, because they're moving so quickly, may be at one end of the molecule, and that is depicted below, where the red section of the molecule is where the electrons are, and the blue section of the molecule is where the electrons have migrated from. This is just randomly occurring, and it's instantaneous. It doesn't last for very long. However, when this happens, any nearby molecule is going to feel that separation of electrons, which will manifest as a charge. Where the electrons are in the molecule, that will be a partial negative, and where the electrons have migrated from will be a positive charge. So this positive charge is going to attract electrons on a nearby molecule. So that's what we mean by induced dipole. This instantaneous separation of charge due to the randomness of electron movement causes the separation of charge in a nearby molecule, and so on. And the more electrons there are, the more frequently this happens. So this graphic here shows how nonpolar dispersion forces work.